Hi Saints, this is Mr. Matthew Lim speaking. Today I'll be delivering the fourth lecture on DC circuits. There's only one objective: recall and solve problems using the principle of the potentiometer as a means of comparing PDs. Okay, let's look at the lecture notes. Before we go into potentiometer, here's a table comparing ideal and practical voltmeter as well as ammeter. Now, in practical, we use a real voltmeter, and therefore a real voltmeter is never ideal. So we call it a practical voltmeter, and and we know that a practical voltmeter draws a small current from the circuit, and because it draws a small current from the circuit, it reads a PD that is smaller than the theoretical value. So as for ammeter, ammeter, which is used in our practical, has a non-zero PD across its end, right? So it reads a current that is smaller than the theoretical value. So this one you have to know, because the meters that we use in the labs are never perfect, all right? So how are they connected? The voltmeter is connected parallel to the component, and the ammeter is connected in series with the component, right? So you can read the details yourself. So I want to get into the concept of potentiometer, but before I explain potentiometer, I want to link it to what you learned earlier in the last lecture, all right? Um, that is, first, you must know what a potential divider is. A potential divider divides PD of a certain source. Like for example, if the battery source is 12 volt and you have two resistors in series, then using Kirchhoff's second law, E is equals to V1 plus V2. That means the EMF 12 volt is divided into two parts, and I can actually divide it in various ways. For example, 6 plus 6, or it can be 8 plus 4, all right? And it can also be 10 plus 2. So there are various ways to divide the PD into two parts, but they will always be added up to 12, all right? Because a potential divider divides the EMF into two parts, all right? The two parts may not be equal. Now, potentiometer actually consists of a potential divider and an ammeter. I'm going to highlight the part which is the potential divider. Okay, this part is the potential divider. Now, it may not be obvious to you. Okay, you see, why I call this a potential divider? Well, I'm replacing the two resistors with a resistance wire. So suppose I replace these two resistors, okay, with a resistance wire. So I take the blue one as the resistance wire AB. Okay, so this time, if I tap 2 points, I tap this point and this point. Okay, so there is a PD across AJ. This point, I call it A at the end, and then the sliding contact, I call it J. So this is a sliding contact. The middle one is a sliding contact. So this is a very clever way to vary the PD across AJ. Okay, so AJ will provide a variable PD. Okay, this AJ can be a variable PD because it depends on where I shift my jockey J. Okay, J is the jockey. So if the jockey is shifted towards the left, then V1 will decrease. But if the jockey is shifted towards the right, V1 will increase. Okay, so the shaded region is the potential divider. Now, a potentiometer consists of a potential divider and an ammeter. So let me highlight the ammeter part. So this part is the ammeter. Okay, this is the connection here. So these two together form the potentiometer. All right, and then we have the PD source which is the unknown PD. This is the unknown which we would like to find out. So let me write unknown. This is unknown PD. So how do we find the unknown PD? Well, we try to get the balance point here. This galvanometer will indicate the balance point of the potentiometer. Now, as you know, VAJ is variable. VAJ is a variable PD. Now, VAJ can be more than PDV, which is this one, PDV, or it can be less than PDV. However, as you adjust the sliding contact left or right until one point where the galvanometer shows you zero reading, okay? So when the galvanometer shows you zero reading, it means that VAJ is equal to the unknown PDV, right? So that is called the balance point. And L1 is known as the balance length, right? So I said again, by adjusting the sliding contact left or right, there will be a point where the galvanometer shows zero reading. And that is a point which is known as balance point. And when you achieve the balance point, L1 is known as the balance length, right? So the concept is similar to a lever balance. Suppose I have an unknown PD on one side, so represented by a certain mass M, right? Represented by a certain mass M. So what I do is I'm going to um, balance this unknown PDV with known PD. Okay, this known PD, which is VAJ. VAJ is the variable. VAJ is the variable. Initially, VAJ may be small, so there will be no balance. But at one stage, if I keep on increasing VAJ, there will be a balance where the lever balance now is horizontal. When the lever balance is horizontal, then it means that um, there is a balance point. So when there is a balance point, it means that V on the left hand side is equal to VAJ on the right hand side. So the concept of lever balance is actually similar to the concept of potential meter where we obtain the balance point. Okay, so balance point is a point where the galvanometer shows zero reading. Okay, so you will take note of this. This is to obtain the balance point. All right, how do we get the value of VAJ? Well, VAJ is actually calculated based on the potential divider concept. And I will write this way. VAJ is actually the first part, resistance of RAJ divided by the resistance of AB, okay, times the EMF E. Now, if I write it like this, you may find it not familiar. Maybe I can modify this part to make it look more familiar. So I write RAJ over RAJ plus RJB. Okay, so this time it looks more familiar, right? So then this formula is therefore similar to this one, similar to this one. Now, when I balance the potentiometer, my VAJ is equal to L1, which is proportional to RAJ, and then I have L1 plus L2 times the EMF, right? And why is it that I can replace RAJ with L1? That's because they are proportional, okay? They are proportional based on this formula. Resistance is equals to rho L over A, right? So if resistance is equals to rho L over A, then resistance is proportional to L, right? So At balance point, then VAJ is equals to V, right? VAJ is equals to V. So that is why this formula allows you to calculate the unknown PD. This is the unknown PDV. Okay, so you have to take some time to digest this concept of balancing the potentiometer. Now, there are a few things to note. Number one, the polarity of the PD source and that of the driver cell must be the same, and that refers to this one. You see, the polarity of the PD source, positive here, must face the positive here. Both are facing the left-hand side, and the negative polarity here must face the negative polarity. So plus is pointing towards the left, and negative pointing towards the right, so that there will be opposing PD. All right, you need opposing PD to obtain balance length. It is similar to this one, the the balance. You see, the unknown mass actually creates an anti-clockwise moment, and the known mass creates the clockwise moment. So these two moments are actually opposing each other until at one point, if you adjust the variable PD, you can get a balance point. All right. So this lever balance illustrate the concept here that the two polarities must face each other so that there will be opposing current. Right. So that's the first point. This is the first point. The second point is when you calculate V using this formula, right? You calculate V using this formula. The main error actually lies in L1 and E, right? But fortunately, the error in E is very small. Error in E is small because the EMF is quite stable. So the error in the calculation of V comes mainly from L1. Okay, so later part in the lecture, I will illustrate to you how to make L1 as large as possible. Remember, L1 is the balance length. All right, the third point, this is a second point. Third point is potentiometer does not draw current from E1. E1 is the PD source. Look at the PD source. This is E1. If you don't know which one is E1, this is the EMF E1, which is, you can write it E equals to E. Why? Because the internal resistance is low. Or even if there's internal resistance, you will discover later on that the PD and the EMF are equal, simply because when the potentiometer is balanced, there is zero current in the circuit. When there's zero current in the circuit, EMF is equal to PD. Okay, so that is the concept of um, the potentiometer not drawing any current from the circuit. This is unlike voltmeter. Uh, our practical voltmeter draws some current from the circuit. Potentiometer doesn't. So potentiometer is essentially a perfect voltmeter. Okay, let's look at this case when there is an internal resistance here. Look, when there's an internal resistance here, it doesn't matter. Why? Because at balance point, the current is zero, right? We mentioned that the current is zero. When the current is zero, let me write properly. When the current is zero, it means that I times R is zero. When I times R is zero, it means that E1 E1 is equal to V, as what I've stated earlier on. You see, E1 is equals to V here. E1 is equals to V when there's a balance point, because IR is equals to zero. Okay. Now I have an illustration here. Suppose I have two 4-volt battery connected in this way, such that the two potential oppose each other. Okay, the positive connected to positive, negative is facing the other direction. So the current tends to oppose each other. As a result, there is zero net current. So emitter 1 will show you 0 net current because the two batteries oppose each other. Now, let's extend the idea to um, another situation. Suppose we look at this second diagram here. So you have 8 volt as the EMF of the driver cell. And if you notice this, the shaded region is actually a potential divider. It divides the 8 volt into two parts. You have 4 volt across here and 4 volt across the second resistor. Okay, so 4 volt and 4 volt. Okay, so it's a potential divider. And you notice that this is also 4 volt. So if you have 4 volt with the polarity such that this part is positive because of this, because of the driver cell, so X is positive and the PD source here is also positive. So positive and positive oppose each other and both are 4 volts. Uh, PD across XY is 4 volt. PD at the cell at the bottom here is also 4 volt. So this emitter will give you 0 current. Now, what about the emitters in the potential divider A3 and A4? So since it is a series circuit, the current is the same, right? So to calculate the current, I take the EMF divided by the total resistance, okay? EMF divided by total resistance. EMF is 8. Total resistance is 2 kilo ohm, right? Because it's 1 kilo ohm plus 1 kilo ohm, 2 kilo ohm. That gives me 4 milliampere. Okay, that's the answer, 4 milliampere, right? So let's move on. Okay, let's start with example 18. Example 18, I hope you can recognize the potential divider. The top part here is the potential divider, right? This is the potential divider. And you know potential meter is the potential divider together with the galvanometer, this part. Okay? The green and the blue and the green and the yellow part form the potential meter. So you want to determine the EMF of the unknown cell if the balance point is at B. Okay. At balance point, the current through the unknown cell is 0. Okay. So what is the resistance AB? So we have to calculate the resistance AB, right? Resistance AB is actually 65% of 60 because the resistance across AC is 60, right? Okay, 65% of 60. Let me write again, 60, all right? So that will give me 39 ohm, right? So what is the PD VAB? VAB, so that will be RAB divided by the total resistance in the circuit, RAC plus 20, multiplied by the EMF 12, right? So if I substitute the values, 39 divided by 60 plus 20 times 12. So that will give me, if you make a calculation, that will be 5.85. Okay, 5.85, right? So let me erase here. Yes, 5.85. So that is the PD across AB, and this PD across AB is equal to the PD of the unknown cell V. So this is PD of the unknown cell V. So we don't bother about the resistances here. You see internal resistance because I times R is 0. So there's no PD drop across the 30 ohm as well as the 50 ohm resistor. So food for thought. What is the current through the lower cell at balance point? Well, I've just said that is 0, right? And then with the balance length change, or will the balance length change if a resistor of 5000 ohm is connected in series instead with the lower cell. Um, Instead of 500 ohm, if I were to put a 5000 ohm, it's not going to change the balance length, because when current is zero through the lower branch, um, there is no PD drop across any resistors. So there is um, no change, no change in the balance length, right? Okay, um, we have a video here which I will not show you. If you got time, I think it's worthwhile to watch this video yourself. Okay, we have reached the last example for today's lecture, work example 19. You already know the solution given, but nevertheless, it's good for me to go through this briefly. Yeah? So I hope you recognize the potential divider. This is the potential divider, right? And then there is no galvanometer. Okay, I have a potential divider. So the first part, if the contact J, which is a jockey, is placed at Y, the PD across XY is then equal to PD across the cell. On the figure above, marked with an arrow the direction of the current through cell C. Okay, this time Y is not the balance point. Obviously, Y is not the balance point. The balance point is somewhere between X and Y. How do I know? Well, first, let's calculate the PD across XY. Okay, PD across XY is resistance across XY divided by the total resistance. So resistance across XY plus 0.70 multiplied by 3, right? So this resistance across XY is 1.4, right? So 1.4, I have 1.4 divided by 1.4 plus 0.70 multiplied by 3. So if you calculate it quickly, you'll get 2.0 volt. Okay, Vxy is 2.0 volt. So X is positive, Y is negative because of the polarity of the battery, right? So in that case, if this part is 2 volt and the lower cell is 1.5, the 2 volt will tend to force the current through the cell. So if I were to draw an arrow, if I were to draw an arrow of the current will actually flow into the cell. Okay, so that is how the current flow. Part 2, determine the position of the jockey J. Contact is the jockey on XY such that there is no current through the cell. Now, for there to be no current through the cell, there must be a balance point. So probably the balance point is here. Okay, the jockey is somewhere between X and Y. So it means that XJ has a PD of 1.5 volt. Okay, so at balance point, then Vxj is 1.5. Vxj should be 1.5 volt. Now we know that the wire XY has a length of 1.2 meter. Okay, so if XY corresponds to Vxy, then Xj corresponds to Vxj. Okay, so Xy is 1.2. So what is the length of Xj? So Xj divided by Xy equals to Vxj over Vxy. So I can find Xj very easily because this is 1.2, this is 1.5 divided by 2.0. So if you make a calculation, Xj is actually 0.9 meter. Okay, so it's not that difficult. You can slowly decipher this. Right, finally we reach the part where we want to increase the balance length Okay, how do we increase the balance length? To improve accuracy, the position found in 2 should be nearer to Y. That means the position of the jockey should be nearer to Y. The balance length should be longer. Suggest one way in which the circuit above may be modified so that this is achieved. Now, for such a question, you cannot just say increase the length xy or decrease the length xy. The examiner wants to know um, how do you achieve this. So actually, there are two suggested ways here. One way is to lower the resistivity. Lower the resistivity um, by changing the material of wire to another one with lower resistivity. So when there is a lower resistivity of this wire, you change it to one with lower resistivity. So when you change it to a wire of lower resistivity, your VXY will be decreased. Okay, the intention is to decrease VXY. So when VXY has a lower value, then to balance the same 1.5 volt, you need a greater length. I said again, if you reduce VXY to balance the same 1.5 volt, you need to have a greater balance length. All right. So also you can also decrease VXY. You can do that by inserting a resistor here. Okay. You put a resistor here, then the 3 volt the 3 volt will be shared among the 3 resistors. The first resistor, which is the internal resistance, the second one here, and the third resistor is actually XY. So with 3 resistors sharing the same PD 3 volt, then you are able to reduce VXY. However, as suggested here, if, if the question carries a higher mark here, then you should not just say include a resistor in the main circuit like that. Okay, you will not just say include it. You have to tell the examiner that there is a limit to the value of R here. If you look very carefully, there is a limit to this because the PD across XY cannot be lower than 1.5 volt. You see? If you look very carefully, this is 1.5 volt. The PD across XY cannot be lower than 1.5 volt. Okay, that is the lowest limit, and the balance point will be at Y. So to achieve a minimum PD VXY 1.5 volt, then this resistor should be 0.70 because 3 volt 3 volt is shared equally between XY and the rest of the resistors. Okay, so if you have this case, the PD across XY will be 1.5, across PD across this resistor VR will be half of it, 0.75, and then PD across the internal resistance here, V small r, will also be 0.75 volt. So again, you see potential divider in action. That is, this 3 value will add up to be 3 volt. Okay, 0.75 plus 0.75 plus 1.5 give you 3 volt. Okay, that is how potential divider works. All right, we have reached the end of the lecture, and you know today we apply the concept of potential divider in potentiometer. Potentiometer is basically an instrument that compares PD to allow you to find the value of the unknown PD. And a potentiometer consists of two parts, the, um, the potential divider and a galvanometer. So I hope you'll go through the lecture materials again and strengthen your concept. Okay, thank you. Bye.